Hello, everybody. Thanks for joining. I hope you had a really nice lunch. I know I did. I really liked the curry today, especially. As always, be sure to start off with a full cup of coffee, because we have a lot packed into this session on retrieval and re-ranking. But first, just a little bit about myself. Oops, there we go. I'm Sean MacAvaney. I'm a lecturer, which is the funny British way that they name a assistant professor at the University of Glasgow, where I do research mostly on neural information retrieval, but also natural language processing more generally. Previously, I did my PhD in computer science at Georgetown University and Bachelor's of Science in software engineering at Milwaukee School of Engineering. I've got a couple of PhD students and a ton of collaborators, but what I think is, I was going to stop. Okay. I also like to build a variety of different tools to support information retrieval research. So for working with data sets, for running different retrieval pipelines, for evaluating. So if you've seen or used any of these tools, that's awesome. If you don't like them, let me know why. If you do like them, also let me know why. Right. So in terms of the schedule, here we are on Tuesday. This morning, you had an introduction to recommender systems and a session on information retrieval evaluation and user modeling. And now I get to retrieval and re-ranking, followed by the hackathon later this afternoon. This session, what are we covering? Basically, there's two main categories of things that we'll be covering in this session. The first is relevance models. Basically, how do we measure relevance? How do we measure if a query is relevant to, or sorry, if a document is relevant to a particular query, or how do we make this kind of estimation? So in its simplest form, a relevance model just looks like this, right? You take in some query, usually expressed as text. You take in some document, usually expressed as text, and you get some relevance score out of it. Now, that's a super high level. There's loads and loads and loads of research into exactly how this individual component works. What neural network architecture do you use? How do you train it? What particular inputs and outputs? You use kind of extra information. Are you contrasting these between several documents? So on and so forth. So we'll try to unpack a lot of that in this particular lecture. So that's one element. The other element is how do you actually go about using one of these relevance models within a larger retrieval engine? So usually we don't care about scoring an individual document. It's a nice individual unit for our model. But what we really care about is searching over an entire big corpus of documents. So how do we go from this unit that gives us a score, an estimation of relevance for a particular item, to executing that over a huge corpus to give us a final ranked list of the top results or some approximation of that. And there's also loads of research here. What data structures do you use an index to perform this operation? How do you scale this? How do you combine maybe multiple models together into a hybrid system? Lots of really interesting questions there as well, and lots of opportunities for continued research in both of these topics. So by the end of the session, and I will be quizzing you at the end. I hope that you'll be familiar with kind of the main types of relevance models that are out there, the main categories of them. I can't name possibly every single one that exists, but I'll try to put together a framework for thinking about the different types and the different qualities that a lot of these relevance models have. A couple of main strategies have emerged for how to effectively train these relevance models. So most of these are based on neural networks that you need to train. So we'll discuss the main strategies for going about training these. Next, we'll cover, and hopefully you'll be able to understand how these relevance models are used within a larger engine, right? So remember, the relevance model is just the component that makes an estimation of relevance. How do we actually go about using them in a larger engine? So hopefully by the end of this lecture, you'll understand that landscape there. And you'll recognize the trade-offs of the various systems, right? So what are the pros and cons of using this relevance model or that relevance model in this particular engine versus that particular engine? And hopefully, you'll also be ready to apply a lot of these ideas in the hackathon. Shout out to Andrew there. We'll be running that later this afternoon. All right, so let's dive in. Part one, we'll be covering relevance models. Throughout this whole lecture, I'll be using this running example with a particular information need. Let's say some user wants to know how a particular auto racer, Lewis Hamilton, how is his performance during the British Formula One Grand Prix. So they might go to a search engine, type away, say Hamilton British GP, or formulate this maybe as a nicer natural language question. Anyway, the query is just kind of a representation, an instantiation of this kind of more abstract information need that this user has. And there's a variety of different documents in our collection. Maybe we're looking over news articles. Here we have a couple from the BBC. This one in particular talks about an accident or something like that happened in the race, dealing specifically the British Formula One race between Hamilton, who is the person who this person is searching for. So this is clearly related to this particular user's information need. And this one, it's talking about a completely different race. Maybe it's talking about some of the same racers, but it doesn't really satisfy the information. So we'll use this as an example of a document that doesn't really satisfy that. And what we want out of a system, what we want out of a relevance model is we want to be able to determine, given the input of that first document, the relevant one, we want some thumbs up, some check mark that says this is good. And if we pass in that query and the document that isn't relevant to it, we want a thumbs down or cross marker that's bad. We could formulate this as like a probability, right? So maybe a 95% chance or 0.95 is given to the top, the first relevant document. Maybe there's some room to be even more relevant, but this one is pretty good. And maybe the second one gets a lower score. These scales, so these outputs, these scores that are assigned for relevance, oftentimes they are listed as probabilities, but they can really be any scale. The important thing is that for a given query, we want the score of the relevant document to be above the score of the non-relevant. So given the same query input and different documents of varying relevance, we want some higher number for relevant and some lower number for less relevant. The question then becomes, how do we implement this component, right? How do we implement this relevance model that takes in these inputs and gives these particular outputs? Well, we can kind of generalize a whole bunch of different relevance models into this generic structure. Basically, we have, again, we're taking in query text and we're taking in document text, and we perform some encoding over that. So we encode the query into some representation, we encode the document into some representation, and then we perform some combination of those signals together to produce our final score. And there's a bit of notation around this too. So throughout this presentation, I'll be referring to a query as Q and a document as D. There's also other notation here that I actually didn't end up putting out throughout the rest of the presentation, so it doesn't really matter. But anyway, you can think of this as some operation over Q that produces some new representation of Q, and doing the same thing over the document, so building up some new representation of the document, and then combining them together in some way or another. This is all still pretty abstract, and what makes different models different and what makes some models good at identifying relevance or better at identifying relevance or worse at identifying relevance or more efficient or less efficient and so on and so forth come down basically to the decisions that you make in the encoder and the combiner strategies. So I've put together this table, kind of like a periodic table of relevance models, right? Where along one axis, we have the cost of the combination, and along the other axis, we have the cost of the encoder. So one option is to have a really inexpensive encoder function, right? It'll be about as simple as you could imagine. We'll get to in a minute. And a really simple, inexpensive combiner function, about as simple as you can get. You could also choose to spend more on your encoder. You could have kind of a more complicated, more expensive operation to encode the query in the document, but keep a really simple, inexpensive operation to combine them. Or you could have different levels, different complexities, different computational costs of doing that combination in each of these settings as well. So you could keep a really inexpensive encoder, but do more and more and more work in the combination. Or you could also continue to do a lot of work in the encoding stage, but then also do additional substantial amount of work in the combination. But we're getting a bit ahead of ourselves here. So let's look at the first relevance model that we'll talk about, which goes into that upper left corner there. Inexpensive encoder, inexpensive combiner. The encoding strategy used here is about as simple as you can get. It was mentioned earlier on in the first lecture, in the 40-some things you should know about IR, 42, or maybe it was up to 57, I don't remember. So about the simplest strategy that you could have for encoding a query or encoding a document is to just split it into words and count the number of words that you see. So this is called term frequency. And we can think of this as a particular encoding of the document, where the document is transformed from raw text into individual tokens with the values of those corresponding to how many times the word appears. So we'll see here, Hamilton British GP for Grand Prix is split into individual words, and we see that each of those words only appears once for this particular query. And meanwhile, this document, it's much longer, there's many more terms, but we do the same thing, right? And here now we see some term repetition. We see prepositions like the word to appearing more frequently, some important entities that are mentioned, some important people who are mentioned in this news article are mentioned more than once, so you get a higher count there, and so forth. So that's the encoder stage, right? So we can represent the query or the document as this kind of encoding of the number of times that we see each term occur in the query document. And to combine, you could just take the dot product between those two vectors. So you could take the number of times Hamilton appears in the query times the number of times Hamilton appears in the document. So here that's 1 times 3. Same thing with British. So British, 1 times it appears twice in this document. And GP also appears, GP appears once in both. So that gets a score of 1 there to give a final score of 6. So this is about as simple as you can get in terms of computational cost for a relevance model, and it's actually, or variations of this approach, like BM25, are actually very effective at estimating some degree of relevance. And the intuition here is just that if a term occurs in the query and a term appears in the document, and if it's mentioned a lot in the query and it's mentioned a lot in the document, it's bound to be more relevant than a document that doesn't do that. Right, so a lexical retrieval model is one that uses representations based on kind of the raw lexical form of the text, so the words that appeared in the text. And the combination is usually based on overlapping terms, so the terms that appear in both the query and the document are then used to score. There's loads and loads and loads of variations of this approach, tons and tons of research in this area. Some things that are very commonly done are doing things like removing stop words. So in this example here, the word to or the just aren't very important. They're usually never important, so they can often just be removed. Stemming, which takes care of the morphological endings of words, normalizing them. So that's very common. Inverse document frequency is another very common approach to augment this, right? So including signals about how rare a term is in the entire corpus. The word Hamilton is probably much more rare than the word British, just due to kind of the natural frequencies of language. So maybe the fact that this document talks about a really rare word, Hamilton, is a good indicator of relevance. There's all sorts of other normalization tricks and so forth that are a bit outside the scope of this lecture. But this covers all sorts of models like TF-IDF cosine similarity, BM25, query likelihood models, DFR, and many, many, many others fall into this category of basically just matching terms. Does that make sense? Yep. Okay. So in terms of cost, right? The encoder cost only depends on the length of the document, right? All you're doing is taking that document, you're splitting it into words and counting the words. It's really inexpensive. And the cost for combining them, right? So combining the signals from the query and document together into a relevance score doesn't depend on the length of the document. It only depends on the size of the representation. Now, those might be correlated in some cases, but we'll call that O of 1. And we'll see the cost of combination increase as we go along this chart. All right, so what can we do to potentially spend more on the encoder, right? So do something smarter when encoding the documents to improve the overall quality of our retriever. So we'll keep a really inexpensive combiner. We'll keep this approach of just taking essentially the dot product between these two representations, about as simple as you can get for a combination signal, but spend more on building a much better encoder. And instead of doing something that scales in terms of the length of the document, it'll be the length of the document squared. And if you remember from yesterday's lecture on transformers, this will be a neural network transformer operation that brings in this new cost. Right. So one problem with these lexical signals is that actually they don't do a great job. They do an okay job, but they don't do a great job of measuring overall the importance of a particular term within the document. So for instance, in this example, this real example from the BBC, the word teams occurred twice, so it got a score of 2, which isn't really an important term, right? If you were searching for this document, you know, maybe you'd use the word teams, but probably not, right? So it's actually not that important, even though it gets a higher score than it otherwise might. And documents that are actually really important and central to the idea might not actually get all that high of term frequencies either, right? So British is very central, right? This is about this particular race. So it should probably get a score higher than the word teams. And similarly, GP, standing for Grand Prix, is also very central to the idea of this query, but it just happened to only have been mentioned once. So an alternative that we can do is we can use a neural language model. We can use a transformer BERT or Roberta or GPTX, whatever you want. We can use some neural language model to predict weights for each of these individual terms. So rather than simply just counting up the number of times the term appears, we can go ahead and use a language model and apply a transformation on the top of each of those representations that just predicts the importance of these terms. So for instance, maybe GP for Grand Prix is a really important term in this document, so it gets a very high weight. It's higher than it would get just by counting the number of times it appears. And maybe the word after is just not important at all. You wouldn't use it to search for this document. There's no reason to really include it even in the representation. So this is an approach called DeepCT that went ahead and replaced these kind of raw term frequencies of words that occurred in documents and actually learned them instead. And the reason it's able to do a good job at kind of predicting what's important is relying on all this pre-training and all these comparisons between all words and every other word that occur in the pre-training of these language models. And remember that the self-attention operation here is an n-squared operation, so it scales quadratically with the length of the document. So the longer document you have, the more expensive it is to score. Okay, so that's kind of one problem with simple lexical signals fixed, right? Now we can actually figure out, we can learn which terms are actually the most important in documents. Now we have a new problem, right? This particular document is talking about the British Grand Prix, but it doesn't actually mention the words Grand or Prix, which you might also use for searching for this, right? It doesn't matter that the searcher used Hamilton British GP instead of Hamilton British Grand Prix. They effectively mean the same thing, but this document essentially doesn't get credit for those other equivalent terms from the document, just because they didn't happen to appear. So if you remember back to yesterday on the language model pre-training, there's a trick that's used to train models like BERT, where you basically mask out a word, and at the end of the network, you try to predict what word goes in that missing spot. So here you mask out GP for Grand Prix, and maybe it predicts that word fits that slot. Or excuse me. So maybe it predicts that GP fits in that slot. It's a pretty natural fit there, but maybe the word gron and pre and race and other words could also fit equally well in that spot, or reasonably well in that slot of the sentence. And this is exactly what this language model is trying to do. A language model like BERT is trained exactly to do this kind of word filling in task. And even autoregressive language models too, the decoder style models, are still predicting the next word in a sequence. So they're all essentially trained to do this. What word would be equivalent in this spot, be it somewhere in the middle or at the end of the text. So you could do the same thing, but not even mask out tokens, right? So we can reuse that same component of the language model that just predicts words, and replace that out and use that as kind of an expansion approach for finding additional words that actually somebody else might use to search them. So you can use that exact same language modeling component and predict that summoned is, probably the word summoned, but maybe also requested fits nicely there, maybe notified fits nicely there, and so on and so forth. So you can actually use this language modeling head of this network to make a prediction of what words fit in that slot. And if you do that for every token in the entire text and do some pooling over that, right? So maybe taking the maximum value for every word in every position, you can end up with actually a really nice representation that captures not just the words that occurred in the text, but actually similar words that somebody else might search for that could fill in that same slot in the text as well. So in this example, we see GP, but now we also see Gron and Prix and Silverstone, which I guess is the racetrack where the British Grand Prix happens, and other related words. So this is one approach, is to basically do this expansion on every individual token to predict basically the importance of the words and other related words that might fit in there. You could also do this just for one token, right? So you could take and use the CLS representation, that initial first token representation, to represent the whole document, and just ask that to predict basically all the words that should go in this text. Right, so broadly, this family of approaches is called Learned Sparse Retrieval, or LSR, and personally, it's one of my favorite areas of work in this area. Basically, it builds up representations that are learned and aligned to a particular lexicon. So you can draw a lot of similarities between this and the traditional lexical term matching search. It's just now we're being smarter about how we assign the importance of each term. Instead of term frequency, we're using learned scores. And instead of relying only on the terms that appear in the document, we're letting the language model predict other terms that are likely to also be relevant. There's all sorts of variations here as well. You can choose to weight individual tokens or not. There's different ways of doing expansion. There's also different ways to ensure that your representations are sparse enough. If you do this in kind of a naive way, you end up with just a huge, big, dense representation of every possible term as your representation. And that's not particularly efficient to search over, right? So there's approaches for sparsifying this as well. So you're not dealing with a huge, huge representation. You're dealing with a representation that only contains the particular terms, or only contains non-zero values for the terms that actually matter to the query. And there's a whole bunch of really common LSR models. Probably the most famous is called SPLADE, which basically does all of this, combines all of this together. All right, so we have now an approach that encodes in quadratic time and combines in constant time. This actually belongs to a larger family of models that fit in the same slot. So generally, we call what fits in the slot to be a single vector biencoder. So the documents are represented as a single vector, and the queries are represented as a single vector, and they're combined together. For LSR, this happens to be a sparse vector or sparse representation. But there's another kind of representation that we could use here as well if we wanted. So I kind of went over this bit maybe a little quickly before, but this unit of predicting basically what word fits in the slot for a language model, right? So predicting other terms that could appear. This operation actually looks more like this. So At the end of your neural network, you have some representation, some contextual representation of what this word or CLS special token means in this particular context. And you have a huge embedding weight matrix of all the terms in your vocabulary. And you basically just take the dot product between those to build up this new representation of the terms that might occur. So you start off with this contextual representation, you multiply it by this embedding weight matrix, and you get out each individual term. Now, if we have this, why don't we just use this nice representation that kind of encapsulates the whole meaning of this text? Why don't we just use this directly? So this is exactly what a single vector dense model does. You could take that first representation of the neural network, right? So of your BERT model or any language model, and use that as kind of a representation of the meaning of this whole text. So instead of representing the text as some sparse vector that maybe you could interpret what the individual dimensions mean, now instead you're representing it as kind of a fixed dimension dense vector, something like 1,000 dimensions or so in most models. There's a slight variation of this too. You could actually take the individual representations of each individual token and perform some pooling operation over those. So for instance, taking the average over each dimension, so performing mean pooling if you so choose. That's another common variation here is rather than just taking that first initial vector, you could take all the individual vectors and take the average. The intuition here is basically just that the document is represented as kind of the average meaning of everything within the text. All right, so once you have that, you can just push this through the rest of the machinery that we already have, right? So we encode the query as a dense representation, we encode the document as a dense representation, and then we combine them together using dot product or cosine or whatever your favorite combination of function is. Right, so a single vector dense model here uses representations that are learned as fixed size dense vectors from your language model. And the combination is as a similarity or distance function between those vectors. There's a ton of variations here too among these models. So for instance, you could do CLS or mean token pooling. You could do combination. You could use different functions for combination, like the dot product or cosine similarity or Euclidean distance. You can represent the encoder of your query document as the exact same network, or you could even use two different networks to represent the query or the document, which could give certain advantages in different situations. Maybe the kind of information you need to encode about a query is different than the kind of information you need to encode about a document. And there's actually like a ton of single vector dense models, but they really mostly vary in their training procedures, not kind of these architectural bits themselves. So when preparing the slide, I basically just took two representative examples of a model that uses CLS pooling and one that uses mean token pooling. Don't worry, we'll get to training later in this lecture. All right, so there we go. We have this first column of our table of relevance models complete. We have simple lexical models that represent documents simply based on the terms that occur and the frequency by which they occur. And now we have dense and sparse single vector bi-encoder models that are able to represent the meaning of text in kind of a learned way. So we're able to learn the signals that are valuable for determining. Up to now, the combination cost has been a function of the representation size rather than a function of the document size. But we can actually do better. We can do a better estimation of a document's relevance to a query if we allow the cost of the combination to scale with the cost of the document. So if we're willing to spend more on this combination phase, if we're willing to use a larger combiner function here, we'll ideally be able to perform a better estimation of relevance. So now we'll look at these quadrants here. They're not quadrants, there's 8 of them. What would you call that? I don't know. Anyway, remember from a couple of slides ago, we were talking about how we can encode each individual token in the text as a dense representation, right? So we can have each word, its meaning within the context represented as some dense vector. Well, why don't we go ahead and use all of these combined, all of these concatenated, this kind of dynamic length representation, depending on the number of terms that occur in the document. Now we have one term per, one vector per term that occurs in the document, and use this as our document's representations. So we can use this directly, right? So we encode Hamilton British GP. We get a couple of vectors out there. We have Hamilton British GP and a separate dense representation for each of those terms. We can do the same thing for the documents, right? We have now 100 or 200 individual dense representations for each individual term that occurs in the document. Okay, this seems reasonable. It seems like there's kind of more information now encoded. We might be able to make a finer grained distinction of relevance now that we're trying to compress the entire document into a single representation. If we're representing each document as kind of multiple vectors, you can see how we might have more capacity to perform relevance estimation. The question and challenge then becomes, how do we go about actually combining these together, right? We can't just rely on a simple dot product anymore because we have representations of different sizes, right? The query is short, the document is long. You can't just take the dot product between those two. One strategy, so one thing you can do is you can take what's called an interaction or similarity matrix between each of those vectors. So here's an example. Here you have the representation for Hamilton as it occurred in the document, and you have the representation of Hamilton as it occurred in the query. And you can take the dot product or cosine similarity between those two representations. And if you do the same operation over every single combination of every term in the query and every term in the document, you end up with this matrix that kind of shows almost like a heat map way what terms are similar to what other terms. So rather than representing the combination of the query and document as kind of these simple dot product between the whole representations, now we're doing the individual representations and all pairs between them. And when you look at these similarity matrices, when you look at these for actual documents, you see some usually pretty interesting patterns. When it's talking about the same thing, you get some nice hotspots in this matrix. And when it's talking about different things, you see less similarity overall in this matrix. All right, but I mean, we still haven't really combined anything, right? Now we just have this matrix. We've done a bunch of dot products. What do we do with it? The frustratingly simple thing to do is to just take the maximum among each query term and use that as kind of your representation. Sorry, use that as your final relevance estimation. This is an operation called maxsim. Basically, you just take, you find for each query term, what's the maximum similarity between it and any other term that occurred in the document. I use that as kind of how good this query matches this term in the query. How good this document matches this term in the query. Do this the same thing for every term that occurs. So Hamilton matches this really well. British matches this maybe not so well. Maybe it's not mentioned in this particular document. And neither is GP. And then you take these individual scores and you can just sum them up and use this as your estimation of relevance. So this is a family of models that have historically been called interaction models. And when you use them with contextualized representations of the query document, they're called late interaction models. And the idea here is to apply some lightweight interaction combination function over these per token query and document vectors. So you have kind of dynamically linked representations depending on the size of the query and the size of the document. And then you combine them together using this interaction matrix, right? So using the similarity between each item. There's lots of variations here. Again, you can combine using something like maxim or kernel pooling. You can encode using a language model or even static word representations. And probably the most famous model in these categories is Colbert, which is a model that does language modeling, encoding, and maxim pooling. All right, so that fills out this column here, right? So now we have a version of a combiner that's about as inexpensive as you can get, a dot product. It's very efficiently implemented, not much to compute. We have now one that scales the cost with the size of the representations. As you get longer and longer documents, it costs more, but you're able to get kind of a finer grained estimation of relevance. Let's go ahead and spend even more on combination. Like let's push this and keep on seeing how far we can get here. So up until now, we've been encoding the query and document separately, right? So we take the query, build some representation. Most of the work then is in this part of the encoding of the encoder here. So take the query, encode it into some representation, take the document, encode it into some representation, and then apply some relatively inexpensive combination function, right? We're talking either maxim if it's something like a late interaction model, or dot product if we're talking something like a learned sparse or dense model. So an alternative is to actually just combine these together, right? So rather than encoding the query and document separately, we can have an inexpensive encoder, which just tokenizes the text. And the combination function now takes kind of most of the work that goes on. So essentially you take the raw text of the query, concatenate it with the raw text of the document, and let the whole neural network, let your BERT model look at every single pair of tokens between the query and document, and iteratively apply this the self-attention transformer network in order to estimate relevance. So this is an approach called cross-encoder combination, right? So you're using a cross-encoder model that lets the signals between the query and document cross one another to build a very fine-grained and frankly strong estimation of a document's relevance to a query. Right, so this goes by a whole bunch of different names. The one I'm going with in this slide refers to this category of models as mono relevance models. So it uses cross-attention between the query and document to combine the signals to build up its relevance estimation. It applies actually minimal work in terms of separate representations. It's just basically tokenizing the query and tokenizing the documents. There's basically no cost or very little cost in terms of the separate representations. All the work happens really in the combination function. And it scales with the length of the model, or sorry, with the length of the document. So as the document gets longer and longer, it becomes more and more expensive to score because of this cross-attention, right? Every token is looking at every other token. Again, here, there's tons of different variations. You could choose to use an encoder-only language model like BERT. You could use an encoder-decoder model like T5. T5, you might choose to generate a token to predict it, or you might just use the probability distribution, or you might choose to throw out the decoder entirely and only use the encoder-decoder's encoder. All sorts of stuff going on there. You could use a decoder-only model like GPT in order to make this prediction. So architecturally, there's lots of variations that have been tried there. You can do things like prune out attention. So you can skip some relations, right? So you can say maybe the query doesn't need to attend to the document, or the document doesn't need to attend to the query in all cases, or somehow limit what tokens are allowed to attend to which other tokens, and so on. You might also choose to have different size models, right? So you might be able to have a reasonable estimation of relevance with actually only a couple of layers of a transformer instead of the typical 12 or 24 layers of a transformer. And once again, there's lots of common models here that you'll probably come across if you're doing work in this area. Things like mono-BERT, mono-T5, rank T5, et cetera, et cetera. Right. So now we filled in this square now, right? So we have an encoder, a really inexpensive encoder that just tokenizes, but a really expensive combiner function, right? So expensive to predict kind of the relevance between the query and the document. Not a whole lot that you can do separately. Most of it is with respect to the query itself. There's a small category of these kind of late monorelevance models where you can actually do some of the computation for the query and document separately, and then continue to do more of the computation together. So this is an approach like Preter, which goes ahead and encodes part of the query in its own network and part of the document in its own network, and then combines those two representations into a final combination. So that's an approach that both spends a lot in terms of the encoder, right? Because it's there. The encoding time is dependent on the length of the document, as is the time to combine the signals together. All right. This has been hinting at we can get even more expensive here. And I didn't exactly know how to do this in proper big O notation, so I just used the omega greater than O of D squared, because now we're going to think about kind of what other signals we can include in the model that kind of can further let us refine the estimation of relevance. So up until now, we've been asking for some documents, D question mark, we'll call it. Is that relevant to a query? And I'll use kind of the probability notation, right? So the relevance of D conditioned on Q here. So is D relevant to Q? For some documents, yes. For some documents, no. Another question that we could ask is not just condition on the query, but condition on other documents too, right? So given what you see in the query, and given kind of this extra information that's provided maybe by these other documents that are included in the model, is D more relevant than those other documents? So here now, we can see maybe this document, D question mark, is considered very relevant with respect to these other documents. So, right, Hamilton, British GP, we have a document that talks about that. We have a document that clearly doesn't talk about that. We can give a very high score to this particular D question mark as a result. But maybe if there was a actually much more relevant document in that pool, maybe there was a document in your corpus that related exactly to this information indeed. Hamilton's results in the British F1 GP, right? Very related to the query. Maybe kind of given that context, maybe actually D question mark isn't that great of a document type, right? This probably more directly answers the question. Maybe this isn't as good of a result to show. So maybe then you would get a lower estimation of relevance kind of with the knowledge of other documents that exist, or the knowledge presented by other documents. Or maybe there's some information in some other documents that let you kind of connect up dots, right? So maybe the model doesn't know what GP is, but one of the documents says GP means Grand Prix, and that helps you then estimate the relevance of D question mark. So you could do these kind of individually, right? So you can estimate D question mark with respect to other potential contextual documents. In practice, you could actually just do this all in parallel with one another, right? So given this list of documents, right? So given 10 different documents that we're sending to the model all at once, how relevant are they with respect to one another? So here now we're building up kind of individual estimations of relevance, each one conditioned on the other documents that appear in that context. What does that look like? Well, the simplest approach to doing this is simply to concatenate the raw text representation of the query, the raw text documentation of each of the documents, and combine them together and produce some relevance score. Or if you're scoring multiple documents at a time, you could have several relevance scores outputted of this one for each individual document. This is a family of models that goes by a couple of different names along the lines of the mono terminology. We've got duo. So if you have a query and a document and then one contextual other document that you're trying to predict relevance with, you would call that a duo. And if you have many more potential documents that you're trying to estimate the relevance of all in the same network, that's sometimes called listo. So that's what I'm calling it here. Or if you run out of space in these little icons, I just call this duo plus. So these use cross attention between the query and not just one document, but multiple documents, which is why it's more expensive than scoring a single document at a time, because you kind of use this extra context from other documents. There'll be more on this in the large language models for ranking sessions, so keep an eye out for that. But there's several common models in this area, things like DuoBERT or RankGPT or PE-Rank and others. PE-Rank is one that applies kind of a late strategy to the same thing, where you partially compute the representations of each document before you further combine with respect to all other documents. All right, so that completes our table of relevance models. We've gone from representing documents as basically just counts of the number of times each token appears, all the way to very complicated estimations of relevance based on other potential documents in your pool, and actually kind of everything in between. So a lot of this space has been pretty well explored. And there's even more on the left side, right? So you can continue to push this to the left. You could have a relevance model that doesn't take any time, or doesn't do any combination, and just tries to make an estimation of a document's relevance to any query that could exist. So that's stuff like spam filtering or quality estimation or other approaches there. In general, this family of models that include single vector representations like LSR or dense retrieval models and late interaction models, these are often called biencoders. Sometimes biencoder is used to refer specifically to this dense variation there too. So it kind of depends on terminology. Literature is sometimes a bit sloppy with the naming. And then I would say in general, this family of models here that include some combination of including both the query and document together at the same time in a transformer network are often referred to as crossover. Now, what are the trade-offs between all these different models, right? We go from something that's really inexpensive to something that's really expensive. Why would you want to do that? Well, all of this is with a lot of caveats that I'm making generalizations here, but generally, as you go further to the right, you get stronger relevance estimations, right? So using a transformer to predict the relevance between a query and document, it gets to see both the query and document at the same time. That's able to produce a stronger relevance estimation than just counting the number of terms, or even doing basically just one layer of this late interaction. Similarly, of course, if you include additional context information, you're often able to get stronger relevance estimations than if you don't. What's the downside then? Why don't you always just do things over here and skip the area on the other side entirely? Well, there's costs, right? So when estimating relevance for a particular query document, it's much lower on the left and much higher on the right. So cost increases as you go to the right here. Again, in general, you could theoretically have a model that is very shallow, but a duo plus model or something. But generally speaking, more expensive, less expensive to predict a single document's relevance. There's also interesting things in terms of generalizability. So in general, models that use kind of less expensive, less complicated combination functions are less generalizable to other data sets, to other tasks, etc. And the ones that are able to kind of make more fine-grained comparisons between the query and document and other contextual documents, they tend to generalize better to new collections, new tasks, new data. And continuing on, again, in general, and depending now on the engine, which we'll get to in part 3, things on the first row here tend to have a lower storage cost. They tend to produce smaller representations or no representations at all to speak of, and higher storage costs when you have kind of more expensive encoding strategies. And in terms of indexing costs, again, depending on how you choose to run your engine, the relevance model here is independent of how it's actually used. But in general, you can have lower indexing costs when doing things on the first row, and higher indexing costs for things on the second. All right. Any questions up to this point? No? All right, I'm going to, oh, yeah, go ahead. Yeah, so there's two main strategies that people do there, right? You can choose to basically take the expansion over all individual tokens, and then you need to aggregate them somehow, right? So you expand over every token, and then you take maybe the maximum for each individual token for your final representation. So that's one strategy, every token. The other strategy is to just base it on a single token, like the classification CLS token. And Right. So you let the model, you let the representation expand every token. And then in the training process, it learns, oh, actually, we don't need to expand the word and to but and or and stuff like that. Right. So although they're similar words and you would expand them, they actually don't matter. So in the training process, it just learns to give them all zero. So yeah, you do expand every token in general, but the network itself learns to basically downweight the ones that don't. Good question. And right, so if we go back a few slides here. More than a few slides. Here, right? So the generation process is really just this single matrix multiplication, right? So you have your representation for each token, and you multiply it by the embedded matrix to then figure out. So that's actually, compared to everything else happening here, that's actually not all that expensive of a step. No, you can do this all in parallel, right? So you do all the tokens all at once, right? You're not masking anything. You still can predict the missing tokens on a word that already appeared in the text. That's one of the strategies actually when training BERT is that some tokens are randomly switched to other tokens. Yeah. So it's doing the same thing, right? You don't need the mask token to do this. Yeah, I haven't seen anything published specifically on decoder only networks on this, but yeah, it would be the same cost, right? I guess you would have to do like you're predicting there the next token, so everything might be shifted by one or something like that. But like BERT encoder networks actually work really well on this. Yeah. Yeah. Hmm. Yeah. Maybe that would work. I don't know. Hmm. In practice, yeah, right. So we'll get to actually like deployment engine stuff later on in this lecture. But there's all trade-offs, right? So you can basically trade off your effectiveness and your efficiency however you like in your system, right? If for your particular tasks and your particular engine, you think you need Colbert to do a good estimation of relevance, right? Well, then that'll come with its own cost for an individual document, right? You can't really get away from that estimation cost there. Then the question is, how do you choose which documents to run that with? And that's what the larger engine decides. Mm-hmm. So you mentioned. Mm-hmm. So I think in practice, we do see that cross encoders, you can do their cross encoders sometimes. But in practice, if you are doing retrieval, that's again part three. Yes. So any model can be a retriever, any model can be a re-ranker, right? It just depends on if you're willing to accept an approximation of the top results or if you want the exact top results and other operational considerations. What data structures you're willing to keep on your index and so on and so forth. Good questions. All right. Oh, yeah, sorry. I didn't see you. Mm-hmm. So there is crossover between the literature, but the naming, I just went with some set of names. I gave other names for other things in the slides too, right? Like people call these things all different things. I think the naming conventions in the space are a mess. So yeah, yeah, a lot of the work is you know, or at least some of the work is shared, right? So there's some crossover, but yeah, I acknowledge that there is a bit of community siloing too that goes on, and similar things that are discovered between different disciplines. All right. Let's see. Doing okay on time. Let's see. Right. So moving on to training. Right. So we have this generic relevance model structure. We have encoder and decoder. Sorry, we have encoders and combiners. And each of these are usually represented as, or often represented as, some neural networks with some parameters. Right. So how do we learn these parameters for these retrieval models? Well, one option is to use human annotated relevance data, right? So we can ask a human to sit down and say, for this query, imagine what you were thinking when you searched for this query, and say, this document would satisfy it. I would want this in my result list, or this wouldn't, and so on and so forth, right? So you can do typical annotation here, where maybe sample number one, you have query, Hamilton British GP documents, this document text, and some numeric labels. So one meaning relevant, or zero meaning not relevant in this case. Uh-oh. There we go. Okay. Oh, sorry about that. Don't need to scroll through the slides like I was before. Well, that's going to be annoying. Anybody know how to turn this off? CC? Oh, there we go. Okay, there we go. That would have been horribly distracting. All right. Right, so we could ask a human to annotate this, right? So take samples of this, label them, be relevant or not relevant, and then we can train a model like we normally would, right? So we could, we have inputs, we have an output that we expect, right? So we could use essentially a pointwise training strategy to give an estimate of, you know, this document is relevant, give this a score of 1, this document is not relevant, give this a score of 0. There's all sorts of different loss functions here. Here's an example. You could use mean squared error, right? So just the square of the difference between your predicted value and your label, which is either 0 or 1 if it's relevant. So yeah, that's one possible strategy for optimizing one of these neural networks. Basically ask a human to label the data and then optimize directly for that label. Now, that actually that's not used all that much in practice because what really matters, it doesn't really matter if you're able to identify exactly this document is 100% relevant and this document is 0% relevant. What matters more is actually that this document is more relevant than this other document. So this is kind of seen as a contrastive problem, right? So given this query, contrast these two other samples, right? This is more relevant than this. So an alternative way to construct the training problem is instead as these training triples, where you say you have a query and you have some document that you know is relevant and some document that you know isn't relevant. And now your training objective is instead to push the score of the relevant document above the score of the non-relevant. So that might look like this, right? So you take it, so for an individual training triple, you would pass in your query, you pass in the relevant document. Separately, you pass in the query and the non-relevant document. And then essentially you're taking the difference between those and you're trying to maximize the difference where the relevant document is getting a higher score than the non-relevant. And this is typically done through cross entropy loss, like the example here shows. So the main idea, right, is that you're basically trying to optimize the relative scores between the documents instead of the absolute scores. And kind of this pairwise training approach tends to be what works better in practice. As a side benefit, when doing kind of this pairwise training approach, there's this trick to kind of multiply your training data kind of artificially, right? So if you were to just apply this approach naively, this pairwise training approach naively, you would take some query, you'd give one positive document and then one non-relevant document, so one relevant and one non-relevant document, and you would go down, query 2 would then have document 3 and document 4 as its positive and negative, and so on. In practice, all these other documents in this particular training batch probably, most likely, aren't relevant to the first query, right? They're probably just random documents if you shuffle the data, and they probably don't really satisfy the information. And in the chance that they do, it doesn't really matter all that much, right? You can have a bit of noise in your training process, right? Especially considering how unlikely a false positive would be in this set of other documents. So the strategy of in-batch negatives is to reuse the other documents in the batch as additional negative documents when training. So instead of contrasting just with the document for this particular query that you think isn't relevant, you also contrast it with everything else in the batch that you think is relevant. So query 1 gets document 1 as positive, and then all the rest is negative. Query 2 gets document 3 as positive, and all the rest is negative, and so on and so forth. Now, this is really useful when the encoder is large and the combiner is small, right? Because you actually only need to encode each of these documents once, right? You're just encoding 8 documents here. You have those representations. And each query once. And then if you're just smart about how you do these comparisons and build up the loss function, you're able to do all those combinations without running all pairs of data through your network. This doesn't really work so well if you're training something like a cross encoder, where now all of a sudden you need, a combinatorial number of pairs of documents when to run through the entire network, right? So, yeah, when the encoder is small and when the encoder is large and the combiner is small, this trick of in-batch negatives works pretty darn well. Another really common thing that people apply in practice, you'll have pairs of queries and relevant documents without actually knowing what isn't relevant, right? So for instance, let's say you're running a search engine and you're using click data or purchase data or something like that to estimate what's relevant or what isn't. You know what's relevant, but you don't know what isn't relevant, right? Even data sets, even like human annotated data sets, some ones like MS Marco, actually only label positive documents. We actually don't know from MS Marco which ones are not relevant. They provide some hard negatives, which we'll get into in a moment about what that means. But those are just kind of inferred from data. So in practice, negatives are sometimes actually harder, and there's kind of more interesting computer science problems to solve around how to pick your negative documents. The strategy, though, is relatively simple. Basically, you just run some other engine over the query, and you have maybe your known relevant document. Maybe it isn't at the top spot. That's, I guess, why you're training this. If it was already at the top spot, you'd have a good engine already, right? But let's say you have another engine that ranks it maybe third. You could use all these other documents as non-relevant samples, right? So you can treat these as additional negative. As opposed to just randomly selecting documents for your corpus or using something like in-batch negatives here, there's some relatedness of these negatives to the query, right? So there'll probably be like some term overlap or something like that. So that's actually a positive, right? Compared to just random passages, you're getting a stronger negative signal by doing this. But you also have a possibility of false negatives, right? So maybe document 1 here is actually relevant, but you didn't realize it, right? So it's mislabeled as negative by using this sampling strategy here. Now, maybe you choose to maybe not take all of the negatives and just take them from the bottom half of the list or something, so it's related but not too related or something like that. So there's some ways around kind of that false negative problem too, if you're willing to play around with that a little bit. But another approach that people use to kind of overcome this false negative problem is an approach called distillation. In distillation, what you do is you train a model to mimic the results of another engine, right? So you take your query, you have another model with a corpus, and you get a list of documents. And each of those documents, again, since we have a relevance model, we have scores for each of those. So we think that document 1 here has a score of 0.95, document 2 has 0.82, and so on. So you could use these scores as your labels instead of human annotated labels, right? So you can essentially tell when you're training your model, you could use those scores as your ground truth instead of real labels there. An example of this would be KL divergence loss, right? So you can normalize these score distributions and compare those distributions with one another. Yeah. Yeah. Yes. Another approach is to, instead of mimicking the scores directly, you mimic the kind of the relative positions, right? So you could say document 1 is ranked above document 3, so we'll use this as a pair. and that's essentially ranking networks there. Now, as you just mentioned, right, the typical strategy here would be to take some stronger model, right? So some model that you trained that might, just because of the model's architecture or something, be able to generalize better and produce maybe stronger labels, train something then simpler from that. So a common strategy would be to, for instance, to take a mono model and to distill a single vector representation by encoder from it. Or also recently, maybe you take a duo plus listo model and fine tune a mono cross encoder from that too. So there's all sorts of strategies. You usually want to go from right to left here on this when trying to distill. Yeah. Okay. I mean, I think that's effectively still just distillation, right? Oh, okay, okay. I see. Yeah. I see. Nice. Yeah, I think that's very similar to the standard distillation, right? Because you're basically trying to then mimic this model thinks this is a high score or higher score than this other document, so treat this as a positive sample. So yeah, lots of strategies here that are all pretty related. But I'll have to check out that paper specifically. Sounds interesting. Okay. Okay. Cool. Um. Right, and I have 20 minutes left, and still a lot to go. But the last thing I want to touch on just quickly is on synthetic data generation. So sometimes you won't have a positive, right? We've talked about ways to deal with missing positive or negative labels. Sometimes you're missing queries entirely, right? So maybe you have a new data set, but you don't know, you don't have any actual user queries on it yet to train anything. So you can use an LLM or other approach to generate synthetic queries that then you can use the rest of these strategies with to further at a very high level. There's actually like a lot of really interesting work in this area, but there's only so much time in this lecture. Right, so in summary, you can use human annotations of relevance when training. You usually try to train your models by contrasting some relevant document with some non-relevant one. It's usually helpful to augment human labels with in-batch negatives and hard negatives when possible. And again, depending on the model architecture and what's easily computable. If you already have a strong relevance model, maybe like an LLM, which we'll see tomorrow, you can use this as a source for distillation, right? So if you already trust the results of one model, you could distill it down into a less expensive one. And if you don't have queries to train on, you can generate them for your particular corpus. All right, questions up to here? Right. Part 3 is on engines, right? So far we've talked about individual relevance estimations, right? So we have a model that's able to predict for a query in general, for a query and a document, some relevance score. What we want, though, is we want to essentially run this over an entire corpus, right? So we don't care about an individual document's relevance estimation for the most part. What we actually want is we want an entire corpus ordered by this relevance score. And not all of the scores, really just the top ones, the top 10 or however many you're going to end up showing to your user or putting into your RAG system or whatever. Right, so how do we go from this top part to this bottom part? There's various different data structures and algorithms to do this, and we'll cover a couple of them in this particular lecture. So we'll cover some data structures and algorithms used by these larger engines that use these relevance models to produce ranked lists. Simplest approach, right? You could just score everything, right? You have a corpus, you have a million documents, you just run the relevance model over every single document. I see somebody shaking their head. That's actually reasonable to do sometimes, right? So like if you have like a strong cross encoder and a limited catalog of or limited corpus, right? It's actually not crazy to just score everything. I was working with a Shopify company that, they have, 100 products in their catalog. We have a really good cross encoder, just run it over everything. It's not that expensive. You get good results. Everybody's happy, right? So this brute force search, exhaustive search can work if you don't need to scale beyond a smallish number of results there. You can also speed up a brute force search using a forward index, right? So you don't necessarily need to compute everything for your relevance model every single time, because we have split out in the relevance model in our framework a separate encoder and combiner function, right? So the representation of a particular document doesn't depend on the query at all. So you could actually compute this all ahead of time into a data structure called a forward index. So the idea here is that during indexing, you take all your documents and you run them through the encoder of your relevance model and store them. So the first document, document 0, has this vector representation or this multi-vector representation or this sparse representation. It doesn't matter. Whatever representation it has, you can just store that. Second document has this representation and so on and so on. So you can just store that into a structure that then you can use for lookups later. During retrieval. So during retrieval, you can then save compute by using these representations at retrieval time. So now you encode just the query, and you can rely on the pre-computed representations of all your documents. If you have a really inexpensive combination function, this can also be fast. So a lot of dense retrieval papers actually just do this approach, right? So when they're reporting numbers for single vector dense retrieval models, it's often just encode the entire corpus, and for retrieval, score everything. So just essentially take every single representation and the dot product between that and the query and score everything and take the top results. And assuming you have an inexpensive enough combination function here, this is actually pretty reasonable too. So this you can score a few million documents in not that long, right? So milliseconds for retrieval, especially on something like a GPU, if you're willing to use that resource. And you don't want to maintain any other data structures or anything like that. If you want something really simple and you don't need to scale above that, this is actually an approach that works just fine. And yeah, I say especially useful here, but really it's only useful if your encoder is large and expensive. Right, so here's one engine, brute force search, optionally with a forward index. This is one nice thing is it works with any relevance model. You can use any model you want with this. It doesn't matter the architecture, it's fine. It'll always give you the exact top results, right? You're not dealing with an approximation of the top results or anything like that we'll get to in a minute. The downside is just not scalable, right? You can't, depending on your model and your time constraints, you won't be able to scale this approach up. All right, we can be smarter about how we choose to retrieve though. So if instead, so let's jump back to these sparse representations that we were talking about earlier in the lecture. Remember, these representations basically just map some piece of text to some sparse representation that says this term occurs this many times, or this term has this particular weight or importance to it. Now, when we score these, it has this really nice quality. These sparse representations and sparse retrieval has this really nice quality that for documents that contain the term, the score is greater than 0, right? So you'll have some positive score here when doing this. There's usually a limitation on lexical and LSR models that each of the individual dimensions is a positive, non-zero. Right, so you'll have a score higher than 0. And if you have a completely random query, Amstel River doesn't relate to this document at all, there'll be no term overlap, and you'll get a score of exactly 0. So this document shouldn't be retrieved at all, presumably. It's just as irrelevant as any other random document. So what you can do is you can use this quality to save lots and lots of compute by skipping documents entirely that don't have any dimensions that match the query, right? The approach there is to use an inverted index. Part of an inverted index is called a posting list. You often see literature say posting lists there. And the main idea is to, while you're indexing, rather than just mapping individual documents to their representations, we map the dimensions, so the terms that occur in each document, back to those documents. So here we see our forward index looks like document 0 has 2, the Hamilton, Verstappen, etc. So that's our forward index. So it says document 0 has these terms. Our inverted index does the opposite, right? It's inverted. It says Grand Prix GP exists in document 0 and exists in document 1. And sometimes you also actually score the you'll store the score there too, right? So you'll say in document 0 it has a score of 1, and in document 1 it has a score of 5, for instance. Right. So these inverted indices basically tell you which documents contain, which terms occur in which documents. And then once you have this, this inverted index data structure, during retrieval, now we only need to consider documents that have matching terms. So in its simplest form, let's say we have the query Hamilton British GP. We only need to look at the documents that occur in these individual posting lists. So the documents that occur in GP, in Hamilton, and in British. If the query was instead Amstel River, you'll have a separate list that says Amstel and River, and you'll only need to look at documents in those. This is about as compressed as I could possibly get a discussion on sparse retrieval to be. There's lots and lots of sophisticated approaches for effectively traversing and retrieving from these data structures. Lots of really good stuff, really, 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 really fast. So being able to leverage this quality of sparsity has huge computational advantages. All right, so sparse retrieval approaches, these are scalable as long as your representations are sufficiently sparse. It gives you the exact top K results, so you're not dealing with an approximation or anything. The only downside is it only works with sparse retrieval models, right? So LSR lexicons. I saw my 10-minute sign, so let's go ahead and relax this constraint here about the top K results. If we no longer care about necessarily getting the top results, we just want an approximation of the top results, what can we do? Well, we can loosen that constraint, and there's a whole bunch of different approximates, nearest neighbor approaches, but probably the most popular one is called HNSW, which is based on this idea of the cluster hypothesis. It says that documents that are close to one another are likely to be relevant to the same queries. So the main idea is to build a new data structure that maps the similarity between individual documents. So this document A is similar to documents B, C, and D. And document C is similar back to A, and then also to Z and stuff like that, right? So we can build up this data structure here that maps individual documents to other documents that are nearby them. Right, so here each dot is a document, and the lines between them are the most similar documents. And in theory, what we could do is we could search this graph, right? We could pick a node and work our way through this graph and find maybe an approximation of the best documents for a particular query. The problem is, if we do that, we'll end up actually just searching the entire graph, or we would in worst case situation. So it's just as bad, if not worse, as just doing a brute force search, because now we have this extra overhead of traversing the graph. What HNSW does is it actually builds multiple levels of this graph. So it subsamples all documents to some smaller number of documents and builds a graph of those. And then it subsamples those into fewer documents and builds a graph of those, and so on and so forth. So you get to the point where you have a layer where you can effectively brute force search some small layer to find the most relevant documents. You pretend your corpus only consists of this one document, and that's the most relevant one to your query, and then hop down to the layer below and resume the search from there. So here, this is the most relevant document. You hop down there, you traverse this graph until you find that this is the one that's most similar to your query, and you hop down again and see that now this one there is the most similar to you. There's no theoretical constraints that this is guaranteed to give you the top K results or anything like that. But in practice, it gives a nice approximation of those results. So you'll usually get pretty similar results to as if you have done an exhaustive search. Right, so that's just one of the very many approximate K nearest neighbor searches that are designed for these single representation dense retrieval models. They're very nice and scalable, but they only give an approximation of the top results. So your effectiveness will probably degrade. Won't find all the relevant documents. All right, last question. Is there a scalable approach that works with any relevance model, right? So the last two that we've talked about were either for sparse only or really dense only. Is there a way that we can apply this to any relevance model that we care about? Well, it's a bit dissatisfying, but this approach of cascading or re-ranking does exactly that. So you can take in your query, you can run a different engine, maybe a really fast one like a lexical sparse search engine, right? To get some list of results, some intermediate list of results, and rescore those with some other model. And you can use any model that you like right there, and you can use a forward index if that makes it faster, or what have you. So you can find ABC is actually better ordered as CAB in this case. And then you return that ranked list out at the end. So this re-ranking approach is nice. It works with any relevance model. It's scalable, right? So you can kind of trade off as much as you want. You can leverage the super effective and super efficient sparse retrieval engines that exist. It only gives an approximation of the top results, though. So you're limited by, right, so you're not guaranteed to get the exact top results that you would if you did an exhaustive brute force search. And you're also limited by the performance of that first stage engine. So if that first stage doesn't retrieve something, you're out of luck, right? So you have to have a retrieval engine there that's good enough. You actually don't, though. So you can have a variation of re-ranking that kind of combines ideas from the approximate nearest neighbor search to kind of augment that process. And there's an approach called adaptive re-ranking, where you start off exactly the same. So you use an engine to get some initial set of results. You then find a new order for them, so CAB. And now instead of just returning those, you look up in that nearest neighbor graph that says these documents are similar to one another. You look up the nearest neighbors of that. So maybe C is close to D, E, and F. And if C is close to D, E, and F, and C is your top result, maybe D, E, and F are actually also good ones, right? So then you can feed that back into your model and score those as well. So now, rather than just scoring what you got from that first stage, you do a actually very efficient lookup of the nearest neighbors and score those additionally. And in this case, I guess E actually turns out to be the most relevant document. It wasn't returned by that first stage, but since it was similar to a document that you rescored as very relevant, you were able to kind of surface that result. And then if you continue to iterate this process, you can continue to refine your search results as needed. So re-ranking optionally with a corpus graph to kind of improve the recall problem of the first stage. This works with any relevance model. It's scalable. It only produces an approximation of the top results. and it requires a first stage engine, but isn't limited by the performance of the first stage engine. Right, so that's a summary of 4 prominent approaches to using these relevance models in practice. We have brute force search, sparse retrieval, approximation nearest neighbor, and re-ranking, each with different trade-offs, different advantages, different disadvantages. All right. Uh-oh. Give it a moment. Yeah, there we go. Right, so when we think about kind of separating out this idea of the relevance model and the engine that it runs in, we kind of see that any model can be a retriever and any model can be a re-ranker, right? It all just depends on what kind of trade-offs you're willing to take, what data structures you're willing to index, what costs you're willing to take up front versus at query time, and so on and so forth. All right, I already saw my 5-minute mark, but a quick wrap up. I promised there'd be a quiz at the end, but it won't be a hard quiz. As a show of hands, are you now familiar with the main types of relevance models? Yes? Yes, good, excellent. Can you describe the main strategies for training them? Yes? Good, that's what I like to hear. Do you understand how they're used within an engine? Right, so you understand the relationship between the engine and the relevance model? Excellent. Can you recognize the trade-offs between various different systems? Yes? Okay, good. And are you ready to apply these in Andrew's hackathon coming up? Yes? No? Oh. All right. Thanks, everybody. Cheers.